Hello everyone, my name is Karthik Narayan and I am from IT Jodhpur. Today I'll be presenting the paper DeePhy on deepfake phylogeny. Deepfakes are synthetic media in which a person's face in an existing image or video is replaced with another person's face. Deepfakes have progressed and look almost realistic as can be seen in these examples. Some deepfakes of Barack Obama, Tom Cruise, and Vladimir Putin can be seen here. Phylogeny is a widely studied domain and is prevalent in the field of multimedia. It is the study of history of evolution in digital media. For instance, here are 8 images which are generated using manipulations from a single image, that is, image A. Images E, F, and H are results of multiple manipulations done in a sequence and are phylogenetic images. The sequences can be seen here in the images A, B, H, A, C, E, and A, D, F. We extend this idea of phylogeny in deepfakes. Firstly, a source image and a target image is taken and a deepfake is created. Further, a deepfake is taken and it is swapped with the face of another target, and the process continues for as many successions you like. In each succession, the generative algorithm used to make the deepfake can be changed, and in this way we can generate phylogenetic deepfakes. Phylogenetic deepfakes are the next generation or an evolution in deepfakes. The idea of deepfake phylogeny refers to generation of deepfakes using multiple generation techniques applied sequentially. Phylogenetic deepfakes are harder to detect and confuses the existing deepfake detection techniques. Deepfake phylogeny opens up new challenges. Firstly, the existing models classify an image as real or fake, but comment nothing about the generative model used to make the deepfake. In past, several events happened where an image video is classified as deepfake using a model, but due to the fact that the AI model used to generate such deepfakes is unknown, there is still an uncertainty whether an image video is fake or not. We name this task as model attribution, which concerns with the correct identification of deepfake generation techniques employed in the making of a deepfake. Model attribution makes the inferred results more trustworthy by finding out the algorithm used to make the deepfake. It enhances the associated confidence of deepfake detection as opposed to black box deepfake detection algorithms. It has several applications in plagiarism detection and forgery detection. This ability to detect deepfakes which have been generated from the same generative model can be useful for uncovering instances of coordinated disinformation spread or other malicious attacks launched using deepfakes. Coming to the next challenge posed by phylogeny of deepfakes. Again, a deepfake is classified as real or fake, but the history of manipulation or the techniques used for generation of deepfake is unknown. Deepfakes now are generated using a mixture of AI techniques and human edits to make it look more realistic. To trace back the source actor and predict the steps involved in making of the deepfakes, this becomes an important milestone for the deepfake research community. In future, research conducted in this direction will also make it possible to reverse engineer the original image from a deepfake. We name this task as sequence prediction, where the correct order of deepfake generation techniques employed in the phylogeny needs to be predicted. And as discussed, it has application in reverse engineering of deepfakes and finding the source actor of deepfakes. There exist big datasets like TFTC and CodeF, but none of them contain phylogenetic deepfakes to support research of such problem statements. To address these research problems and promote research in these directions, we propose a novel DeePhy dataset with phylogenetic deepfakes. As can be seen, we have used 3 generative models to prepare the dataset. Succession 1 deepfakes is made using a single model. Succession 2 deepfakes are generated using 2 models, whereas Succession 3 deepfakes are generated using 3 models applied sequentially. The slide shows the phylogeny tree of the DeePhy dataset. A Succession 2 deepfake uses a Succession 1 deepfake uh, as a source and a real target image and generates a deepfake. And a similar process is followed in the generation of succession 3 deepfakes. The dataset consists of 5040 deepfake videos and 100 real videos and is approximately 30 GBs in size. Each video has 720p resolution and an average duration of 20 seconds. The dataset has total 18 phylogeny sequences with sequence length varying from 1 to 3. The dataset is publicly available and can be accessed from the link shown after the signing of a license agreement. The database is richly annotated and has samples of different age groups and skin color. It also has occluded samples. To make it easier for the research community to use our dataset, we have benchmarked our dataset using 3 evaluation protocols. The first one being the deepfake detection task, where the model is trained in binary classification setting to classify an image as real or fake. This protocol gauges the quality of deepfakes with existing databases. Moreover, the proposed dataset contains deepfakes of subjects with Indian origin. The succession 1 deepfakes of the proposed dataset can be used in conjunction with existing datasets to fill the void of Indian origin deepfakes in the existing datasets. As can be seen from the table, the overall highest detection accuracy achieved is 88.89% by CapsuleNet, and there is still a scope of improvement. The second protocol is model attribution, where the model's potential to identify the usage of a generative model in making of a deepfake is just. It is done by training the models in a multi-label classification setting. For example, the given deepfake is generated by first applying FSGAN and then phase shifter. The generated deepfake has a ground truth of 101 for FSGAN, phase swap, and phase shifter respectively. Here 1 represents that the respective generative model is used in making of the deepfake. The generated deepfake is given input to the model, and the model predicts the presence of each generation technique. There is no necessity for the order of deepfake generation techniques employed to match, but only the presence in the generation process. Like in this case, predicted output for FSGAN and phase swap is matching, but phase shifter is not. We have performed 2 experiments, namely train and fine-tune. In train experiment, we employ the train set of the proposed DeePhy dataset, while in fine-tune experiment, we train on the Face Forensics++ database and fine-tune on the train set of the proposed dataset. As can be seen from the table, CapsuleNet again performs the best, achieving a 90.86% accuracy in train experiment and 87.97% accuracy in fine-tune experiment. Coming to protocol 3, it concerns with the sequence prediction, where the models need to predict all the generative models employed and in the correct order. For this, we train the models in a multi-class classification setting. For our database, we have a total of 18 classes corresponding to each phylogeny sequence. We take the same example as the last time, but this time the ground truth is FSCAN phase shifter, as these are the techniques involved and in that order in the making of that particular deepfake. The deepfake is given as input to the model and a sequence is predicted. The complete sequence should match for it to be a correct prediction. Specifically for this example, the prediction and ground truth doesn't match. These are the results of succession 1 deepfakes where only one generative model is used. These are the results of succession 2 deepfakes, and these are the results of succession 3 deepfakes. It can be observed that as the succession increases, the accuracy decreases. This is because the phylogeny increases with successions. Finally, it can be seen that the average overall accuracy achieved by all the 6 SOTA models are 54.36%. The conclusion is that the existing deepfake detection algorithms perform poorly in the model attribution and sequence prediction task. And in future, the algorithm should be able to perform model attribution and sequence prediction along with classical deepfake detection. The dataset can be enhanced in future with more number of sequences and with a greater depth of phylogeny. Samples of different origin can also be included and not just of Indian origin. As discussed in motivation also, the proposed work also has applications in real-life scenarios of plagiarism detection and forgery detection, which is still relatively unexplored. It can also be helpful for law enforcement agencies to get more information on instances of coordinated spread of disinformation using deepfakes. The future work could include research in the direction of reverse engineering of deepfakes. It could include a possible development of decoder network which can output the original face from the deepfake and predict the algorithms used in making of the deepfakes. In the end, I would like to thank my co-authors Harsh, Karthik and Surbhi. I would also like to thank my advisors Dr. Mayank and Dr. Richa. Thank you for listening.